man take it away.
Yeah,
Mark. Sir, in front, please sit down. Thank you. Thank you. I always want to sit down. So we're going to talk about a lot of different Linux security things today. Does anyone remember the days of shell hosting companies? Did anyone actually have a Linux shell from a shell hosting company? Raise your hand. You guys were all doing piracy, weren't you? So shell hosting companies were 10 years ago kind of what cloud instances are today. They were the easiest way to get access to a Linux box. They were the easiest way to kind of get a presence somewhere on a server that wasn't in your home. And the other thing about shell hosting was there was rampant amounts of fraud. There were rampant amount of denial of service, website attacks, piracy, all kinds of things. So a lot of the stuff in this talk is actually really 10 or more years old, except a lot of stuff still applies. Like we'll go over mandatory access controls and kernel hardening and some other stuff. So a lot of the attacks, we've seen different slight changes over the years, but ultimately we're doing kind of the same things. We're hardening systems in the same ways that we did 10 years ago. There's actually some interesting constraints in cloud computing that shell hosting did or didn't have. We'll just kind of go over some of the different aspects of what you can do, whether you're a desktop user, whether you're in systems administration for a living. Hopefully you'll pull something out of this talk that will be applicable to you. So most successful exploitation isn't about I didn't install my WAF, or I didn't install my firewall, or I didn't deploy X, Y, or Z. It's really a lot of things failed in order for an attacker to succeed. Bruce Schneier, his book Secrets and Lies from 12 or so years ago now, he made the point that security is a process and not a product. And unless you think about security in terms of process, you're ultimately going to get owned because the thing that you're putting your money into or your best effort of security into is going to have a vulnerability eventually. There's going to be a workaround, there's going to be some sort of bypass or whatever else, and ultimately the rest of your infrastructure, the rest of your security controls are what's going to actually keep you from getting exploited. Zero day is one of those things that it has a lot of appeal for news articles and for media stuff, and even in the security community, like the 0 day is like this awesome thing. Like I got a 0 day for this web app or this whatever. Ultimately, like the 0 day doesn't mean much unless you didn't do anything but run that software and hope for the best, right? Like so, if there's a kernel 0 day and there's a local root exploit, if all you did with that system was deploy your kernel like out of the box, that kernel exploit, yeah, it's probably going to work. But there are other things you can do that doesn't make a 0 day mean like the be-all end-all to your security, structure. Defense in depth, and it's one of those few phrases that I find that doesn't make me, nauseous about security. Defense in depth is a real thing. You may see it in a lot of marketing, you may see it in a lot of sales stuff, but it really does actually have an effect. And if you're not planning, going back to the process idea, if you're not planning about security in a process in defense in depth type models, you're probably going to end up in a bad place. The other thing that I found interesting, the last couple of years I've been doing penetration testing, web app security audits and stuff like that, and a lot of customers don't understand that not all attackers are active root or being an admin. Like if you get root on a box and I have encrypted data on there, you still can't inherently just get that encrypted data, right? Like you can't decrypt that data just because you have root. Thanks, Lynn. So root isn't everything. Domain admin isn't even everything necessarily. When you're doing an assessment, it's usually going to be goal-based, and what the goal is probably predicated based on the type of organization you're doing the assessment for. So if I'm going after a bank or a healthcare agency or something else, there are very specific types of data I want or very specific types of access I need to get. But getting a single account on a server may not actually be the goal, even though a lot of people kind of naively think like getting roots would be all end all. So let me put some of these up here. So Linux in general, if you put a Linux box just on the internet and do nothing else, you'll probably be okay. What happens is, we take something like an SSH server and we use shitty passwords. Or we take a web server that's otherwise secure and and we put shitty web apps on it. Like, we are introducing attack surface. And the days of, MSO 8068 or whatever, these kinds of things, even on the Windows side, are really disappearing. Like, remote group exploit type things are becoming very scarce. Things like ASLR and depth and stuff like that. There's a lot more hardening happening out of the box that people aren't really, I think, giving enough credence to. And what we are seeing is, yeah, attacks aren't going down, but that's because we're fundamentally adding new areas to attack. So it's not like we're losing ground in things we've been trying to protect over the years. We're actually gaining ground in a lot of that. But then we're adding new attack surface and things that were not there 10 years ago. So it's this ebb and flow, and it's hard to stay ahead of it. But if you start doing things in terms of the process like I'm talking about, you'll actually see that maybe you won't catch up all the way, but you're probably going to be in a much better place than your competitors or someone else that might be up for an attack. So web apps, a lot of people go, oh, SQL injection, I'm going to steal your data, or your MD5 some password hashes for your users or whatever. That's great, but you can take a SQL injection and pair it with making a web shell, and then wget a local kernel exploit, and then GCC using that web shell, and now you have root. So SQL injection, it doesn't get a lot of attention in the ways it should. It gets attention like, oh, I'm gonna steal data, the end. But you can actually do a privileged escalation with a SQL injection vulnerability. And a lot of people don't talk about that kind of context because it's not a direct win. It takes more effort, it has more steps, but in order for those steps to work, the people defending that system have to not be trying to defend the system from layered type of attacks, right? So if you're thinking kind of that step ahead where what happens if this does have SQL injection vulnerability? What happens if they do get a local shell in PHP running as the Apache user? What happens if they get, and it just keeps tyranny. You have to think about where are we going with that. So there are things in Linux, some of them are built in, some of them we're going to build in. Some are easy to use, some are hard to use. Hopefully you guys will pick some cool things up. We're going to start really, really simple, and we're going to kind of ramp up slowly. Some of these things won't be things that you may want to do, but I want to put some context into things that people do and tell you, yes, this is how you could do it, and then I'll show you hopefully better ways to do it. Because there are a million ways to do anything in Linux to begin with. We can also do that with security, and if we layer one thing in, but the layer is actually kind of poorly done, which you'll see in a second, you may be adding kind of more like to security theater than actually real security, where you think it's good, but ultimately the attacker knows more than you, therefore they're going to defeat it. So each of these, just so you guys know, this is all actual terminal output. I just hate seeing screenshots of terminals that no one can read. So these are line numbers. If you have a question, it makes it a little easier. And someone's actually calling me right now. Good. So file system mount points in Linux, if you're not all that familiar, maybe some of you guys are into Windows or Mac or something else. Well, Mac, hopefully you these mount points, basically most mount points are going to be rewrite. You're going to read data, you're going to write data. No shock there. Temp is kind of the quick win, holy grail for an attacker. Because temp on a file system, on a distribution of Linux, is probably going to be the only place that an attacker that doesn't have any place to actually write files. Like, you have a home directory as an end user. An attacker might be attacking a daemon that doesn't actually have a home directory. It could be doing stuff in memory, have a network socket, and write no data. It could just be doing stuff in memory, and that's it. So if an attacker does find a vulnerability in this daemon that has no, rewrite or no write access to the file system, they need some place to drop code or, stage it or compile from or whatever else. So temp's a really good place to go after. So we see by default temp is rewrite. If I, as an attacker in line 3, run an exploit, no errors were returned, nothing bad happens for the attacker. They probably opened a shell remotely or, did some other terrible thing to my system. If we go to line 6, you can see that we can remount the file system so that when we do the remount, we actually add the no exec flag. And what the no exec flag does is it doesn't actually remove the executable bits from a file. So if I added the executable bit to a binary, when I run the command on the system that has no exec for the file system that file's contained within, it basically ignores the execute bit. What that allows us to do is, if an attacker does get access, if they compile a binary, when they run that binary in temp, it will not run because there's no executable, no execution on that system for binaries. So just so you know, this doesn't get you away from scripts like interpreted, like a Python script isn't beholden to this. So just in case you're wondering, it's like an executable shell script or something, right? The interpreter is the executing part. It's outside the scope of temp, therefore it'll run. But binaries, like a lot of kernel exploits, are probably going to be some like C compiled binary. So if you do this one step, if an attacker gets access through some system service or daemon, but has no write access to the file system, you've just effectively locked down the only place they're going to be able to pop code on that system to execute from. That one layer right away probably stops most of your script kiddies that can actually get that far. So very simple thing, but huge effect because we're thinking about attack surface, not just like, oh, that's a little like simple change, but simple changes can have magnified effects. So setuid and setgid are these special things that probably most of you have never really needed to deal with. What setuid does is, if I have a file that's owned by user root and group root, when I set the executable bit on that, I can actually enable this special flag, if you will, called setuid. And when setuid executables run, they actually run not as the person executing the binary, but actually as the owner of the binary. So in this example, if you just take a quick look, this attacker, random person, has this horrible evil ping command that does only God knows what. What people don't notice out of the box is that the Linux kernel, the networking subsystem, to do ICMP packets, you're actually elevating privilege. So when you run the ping command as your normal, like, everyday login user, you're actually not running it as your user. You're actually running it as root on that system. But it's all transparent to you as the end user. So setuid or setGroupID affects either the user or the group, depending where you add the Uid bit to. What we see a lot of times, and this is more slightly historical, Slackware 7.1, any Slackware users formally? Yeah, 2 people. Slackware, there was actually a Uid Perl root exploit, because remember, if you have executable code that has the setuid bit that's owned by root, if you find a vulnerability in that code, it is no longer a local privilege like, oh, I've owned that account of the guy who ran that file. It's, I have access to root. So you can drop a shell out of that vulnerability and actually get root because of setuid. So over the years, you've seen less and less setuid and setgid binaries on the Linux, Linux distributions in general. Some of them still have them out of the box, and that's fine. Like, a lot of these things have been tested for 15, 20 years now. So, but in a similar way to noexec, if we had the no Uid, all that's going to do is take away the ability to have Uid bits on this file system. So if you had this evil ping binary that had the Uid bit and had to run with this Uid bit to execute properly and exploit the system or whatever, by running no Uid on that mount, you're actually taking away the ability to do that. And if you do noexec, inherently no Uid is implied, because if you can't execute, the Uid bit doesn't matter, or you can just do no Uid. So if you want to be granular about this, you can go ahead. So here's a good example of attackers being done, but not the best way to do security. If we have a bash history, so an attacker logs in, they steal your password, they log into your system SSH, they're bugging up a bash shell. This attacker's dumb, they're bold, so they're just gonna download an exploit, run it, compile it, whatever, and they're gonna delete bash history, because why not? And you're gonna log in and look for the bash history because you've heard like, oh hey, you're attacking my server, Mr. Hosting company. You look for this log file to figure out what the hell is going on, and there's no log file anymore, right? So there's a couple things we can do, and again, this is not, there's a few ways around this that if you want to talk about, we can certainly talk about them, because some people usually yell out, well, what if you did? Yeah, you're absolutely right, I guarantee you. If we change the bash history file to be owned by root, we change the permissions so that root has full access, and then any other user could add content and read content from that file. The chatter flag, or the chatter command, if you will, stands for change attributes. So beyond your normal POSIX, Unix read, write, execute type stuff, there's actually this attributes layer that goes on with it. And the two attributes that any of us probably use on any given system are the append only and immutable. So we're going to use the append only here. So in the context of a history, log history file, append only makes a lot of sense because we're going to add to this, the tail end of this file constantly as the user types in a command, and we want them to read to it, write to it. So all this is still valid for the end user, but remember that root owns this file now. So the attacker goes in, they get their exploit, compile it again, and they think they're clever, so they try to delete the history, and they get an error. Maybe they're a really good attacker. So maybe this attacker knows what attribute flags are. They're like, oh, this sysadmin just decided to screw with me, let me just turn off the chatter for the append only. And when they do that, then they get a permission down on that as well. So not only do you have the attacker doing this bad stuff on your system, but you also have them trying to clean up after themselves on the system. So in terms of seeing an attacker do stupid things because they're rushing to go ahead and actually compromise your system, their lack of foresight to check these things out ahead of time actually leads us to being able to catch them kind of in action. Passwords, despite everything that we keep saying, like, oh, everyone knows how to make a good password and everyone will never do, like, password is a password. And, we all know that's a lie. We all have end users at one point or another that do these horrible things. And, they make contentions after they get compromised, like, oh, I didn't think it was that bad, or I didn't think anyone guessed that word, or like, oh, that's in the dictionary, or, any number of things. So one really, really simple thing you can do if you don't trust your users on a Linux system is just enforce reasonable password policy. This isn't going to save you from all kinds of attacks, but you can at least make it difficult for an attacker. If we think back to all the breaches that have happened, like LinkedIn, for instance, is a really good one. LinkedIn got breached, they got password hashes, they cracked like 40% of them in one day or something, right? We don't want necessarily to have passwords that are like 20 characters, but what we want to do is make the attackers go after the 40% low-hanging fruit and not worry about trying to deal with my 12-character password. Because why would they? They have plenty of targets to go after. So just some examples. This is just a built-in, yum install, pan crack lib, and it'll basically do this interpretation of a password for you and give end user feedback for it. So simple change, but can actually have really impactful results for you. IP tables is really neglected in terms of what people do with it. Like most people just have a basic, ingress firewall rule set. Hey, don't log into, port 22 or don't do this or that. What IP tables can do though, the netfilter subsystem in the Linux kernel actually has a ton of capabilities. So one of which, and I see a lot of people do some weird things to do connection throttling. You can do connection throttling natively in the kernel using IP tables. So what a lot of people end up doing, and there's going to be some more examples of this as well, but what a lot of people end up doing are building these user-land tools to do log parsing and look for multiple connections and vet out whether or not they should block a user based on the number of IP log trail. User-land is slow. User-land is very slow relative to kernel. So anything you can do in the kernel, you should do in the kernel. There's a reason that the firewall is in the kernel. So utilize it whenever possible. In this example, a really simple showing of how to do a basic SSH, brute force block, if you will. You have a counter, which is, I can't see the end of that slide. On line 6, you basically just have a counter within a 60-second window. If you have 4 connections come in, it basically throttles you out. And that's it. There's no cleanup. There's no horribly latent IP tables rule set with 1 million records in it that you'll never be able to go through. There's no fail to ban user land script to parse your log files. If someone's trying to brute force you, they're going to get very frustrated and they're going to go away very quickly. And that's the important part, is we're not necessarily trying to give the best security. We're trying to give the security that's going to make attackers go elsewhere. Obviously, if you're a targeted entity, if you're like a healthcare company, you might want to take some other points of action here. But for a lot of end users that I hear oh, I have all these crazy scripts running in my home system to block out brute force SSH, you could just do this and you'd be done with it and you wouldn't waste any more time. So in your example up here, you can just see 3 connections come up in a row, and the 4th connection never actually completes because that was the 4th connect attempt. Port knocking is a very cutesy kind of feature. If anyone's ever used port knocking, it was probably just for fun. It probably wasn't for a production system. Maybe you did, but most people, it's kind of just a interesting thing, and it's another good example of what IP tables can do for you. So port knocking is an equivalent to prohibition era, speakeasy, knocking on door 3 times in a certain way type thing, right? We know a certain order, a certain combination that is kind of a privileged piece of knowledge where if I do it in this right order, in the right way, in the right manner, they will open the door for me and I can come in. Same thing goes here, except we're using ports. So this is a slightly tricky to follow along. So the check port, which is line 3, is basically the thing we care about. So SSH is what we care about, check port, that's what we need to know. The 2 remove lines and the set line in the middle are very important because the set line actually says hit this port first before you can go to what our check port is. So in this case, I have to open port 1600 before I can go to port 22. So that's the port knock, is I hit 1600 first and then I go to 22, then I'm given access to the system. What's good about the 1599 and 1601 remove that flank this port is that if you're running a port scan, 65,535 ports. I'm going to run some port scan. Maybe it's linear, maybe it's random, whatever. The odds that an attacker are arbitrarily going to scan you and happen to hit port 1600 and then 22 before they hit 1599 or 1601 is a pretty slim margin for that attacker to get lucky. Now you can chain ports as well, but again, this is like one of those things, it's a little bit more overhead than most people want to deal with. But in this example, you can see how well it works. The nice thing about port knocking, and the thing that you should be aware of, is with port knocking, an attacker never knows what a set port or a remove port is. The end user experience of an attacker looks exactly the same like they hit any other random port that doesn't have a listening service. So if I hit 22, they don't get a, hey, you didn't port knock, go back and port knock. Like there's nothing happens. It's like sync connection, hold, that's it. So if we hit 1600, which is our set, and then we hit 22, we're in. We can actually SSH, open the connection, we're good to go. If you go to 1599, it's a remove port, you go back to 22, and they can't get in again. So again, not super practical, but again, if you're doing things like I'm scared of brute force attacks on my SSH server, or I hate getting all this traffic to my SSH server and going through the logs, or there's a million things people get really frustrated for about brute forcing. This is another example of a way that an attacker won't know you have port 22 open behind a port knock. There's no distinguishable information that you as the sysadmin are providing to that attacker, which is great. Another thing you can do with Ivy tables is you can actually do match rules based on host level parameters. So like a user or a group, you can actually make rules specific to a user or a group. Now in a multi-tenant situation where you have, let's say, like the shell hosting company I used to work for, if you have 300 users on one system, you want certain users to go out certain ports, other users not to, certain users to bind certain ports and have traffic come into them, whatever scenarios you can think of, you can actually do restrictions based on that user or group. So if you have a bunch of students on your system, you can make a students group, put that group ID in a firewall rule set, and actually block or allow traffic based on the fact they're a student. Again, this is one of those things, a lot of people do crazy user land things like make restricted shells and do all this ugly stuff to make people not do stuff they shouldn't do. You can actually control that at a user level with the network firewall stack, which is pretty amazing because a lot of people don't know that this is even an option. You can go a step further if you really want to. They have Geoip support. So again, if you don't want brute force attacks or you don't want people from China necessarily logging into your WordPress or something, you can actually do rule sets based on Geoip data from like Aaron and APNIC and similar, which is kind of cool. So in this example, we're actually giving my unprivileged user access to port 80, and we're actually shutting down all of their access. So you can see on line 4 through 6, my root user actually can't use port 80 anymore. But if I drop down my unprivileged user, they can. Because remember, the kernel doesn't give a shit that you're root. I mean, ultimately, that's what happens, is the kernel doesn't care necessarily. It cares what the policy is. And this is not going to be more evident than when we get to the mandatory access control stuff in a second. There's a blob attacks. There's going to be a couple of blobs of text. I'm not going to read them off for you guys. GrrSecurity, what you need to know about GrrSecurity, it's been around for I think about 12 years now. It's a patch set to the Linux kernel to do hardening of various aspects of the kernel. So whether that's network stack stuff, it's user land stuff, there's a lot of different patches. You basically just, if you've ever configured a kernel in Linux, you basically just check features on, check them off, whatever you want to do. So one example of this, if we look at just something simple as opening a port, any port above 1024 by default on a Linux system, unless you changed it, is unreserved, and therefore an unprivileged user can bind, to that port. So if I bind port 1500 for some attack or some bad thing or whatever, that's not a problem for a normal end user. If we look up here, we can see that the Stanislav group has Geoip 1000, and the cool thing about GrrSecurity, once you patch the kernel, it basically enables the kind of kernel namespace parameters, like kernel parameters, like anything else, like IP stack parameters or similar. And you basically can do like real-time tweaking of these policies effectively. In this example of policy, if you use socket server GID and set it to a group ID number, what that's going to do is not allow any actual binding of ports for that entire group. So if we go back to kind of a student example, if we have students that should have never any purpose of binding a port on a system, we can inherently just make one small change with that one kernel tunable option and block out every single port binding from every single unprivileged user for that group. So if you've ever, again, gone to like great lengths to block people from running ports, or like, I know people that have created kill scripts that are like a while loop, and it'll look for people running ports under their user ID and kill it, like, we're way past this. Like, we have really, really good stuff to do, and it's just easy to build into the kernel natively. If you want to take it a step further, which practicality is slightly limited here, but if you want to take it a step further, setting the socket client GID, you have the same effect, except it's not binding ports only, it's actually killing all network traffic for that group. So a good example of this is you have a student lab. I used to be a U of M Unix admin, and I had a Solaris lab and I had a Windows lab that I had to manage for students. So they logged in locally, and let's say they should have a system to compile code on or run like an IDE or something. They don't necessarily need actual access from the network at that point, but the computer itself needs network access, so it's not like I'm going to like turn off the NIC or unplug it from the Ethernet, but I can't actually restrict their user from actually doing network calls just because they're in a certain group. So again, this is all about flexibility, about taking granular controls, layering them up, adding as much or as little as you need. Some of these things are practical, some of them aren't. A lot of you guys probably have client infrastructure that no one ever logs into except for root, and that's it. But if you have multi-tenant systems, some of these features can be really, really important, and they can save a lot of overhead time and writing bad shell scripts and other ugly stuff. So in this example, you can see, hey, I can tell that to Google, no problem, and then at the latter lines, you can see I can't even resolve Google, which shows that UDP 53 traffic got shut down because I can't even resolve Google.com anymore. SE Linux had, this is somewhat timely, but it's more concerning than ever. SE Linux was actually an NSA project. And every time I've given this talk, I've been like, yeah, don't worry, it's cool, like people review this stuff, but now I'm feeling worse and worse about those statements every day. For what it's worth, SE Linux in general has been around for a long time. There's actually a lot of private means that work with them. There's a company called Traces, specifically Josh Brindle. There's a lot of public-private interaction. Again, this is all open source, not to say that that's infeasible, that there's a backdoor in it. Random number generators in this standard in 2006. But you never know what's going to happen. I would say in general, though, I trust SE Linux as much as I need to. And if you don't like SE Linux, there are other things like GrrSecurity actually has a role-based access control part to it. GrrSecurity is definitely not NSA funded in the same way that SE Linux project was initially. So you have options. What I would like to get across, though, as we get into this next section is mandatory access controls is a real game changer in most cases. And hopefully you'll find out why. We have a typical Apache server runs on port 80. We decided we want to change it to run on port 81 for whatever reason. If I go and actually just that top line and sets, just replacing port 80 with port 81 for what port to listen on. If we restart the Apache server, we'll get failed. And when we look at our kernel log, and the bolded parts are obviously highlighted, we see denied, Apache 2, and 81. So we know that, hey, what I wanted to do with port 81 is probably not going to pan out for me. SE Linux implements basically contexts around processes, around user actions, around all kinds of things. Those contexts have policies behind them. The policies enforce mandatory access controls. Discretionary access controls are like your Unix privilege. You own a file, therefore it is up to your discretion who can access that file, what permissions a group has to that file, to your own user, what permissions you have. Mandatory access controls takes up a layer closer to the kernel, where you're actually defining policy that doesn't care about what the user necessarily wants. It's kind of like this overarching policy, and the user can play within under that umbrella, but never exceed that umbrella. So if you were to give me, or I shouldn't say if you were to give me, but if a user accidentally did like, chmod recursive 777 on their home directory, I would then be able to go to their home directory and read and write and execute and delete and whatever else I wanted to their data. Because it was up to their discretion what privilege they allowed, and they did it poorly, so I could take advantage of that. What is important with mandatory access controls is, if they did that, and I had a policy that said, only Stanislav can look at Stanislav's files, that's it. No matter what you do with your discretionary access controls, that top layer of that umbrella is the last thing that I care about and the most important thing I care about. So even if the discretion says yes, the mandatory says no, the mandatory always wins. So you can imagine this is really powerful, that if you have systems with users that make mistakes, this is a great thing to put in. But think about it in another light in terms of the attacker. If an attacker breaks into the Apache web server through whatever means, and they say, oh, I want to write files to this out-of-scope place, or I want to execute a binary as the Apache user from here, or I want to do whatever attacker thing an attacker would want to do at this point, if it's not built in mandatory access control, they are not going to do it. Where the really interesting part of that comes in for the zero-day context of this talk is an adversary doesn't know, or I shouldn't say an adversary, a defensive person doesn't know what attack an adversary may actually launch upon them. But what we do know is that there's a certain like minimum boundary of what we need to do with a certain like service or a process or a context, right? I know Apache needs to serve files up, port 80, do HTTPS connections, whatever. If it does anything outside of that scope, that should be shut off immediately. So you have like a baseline, and if you're outside of that baseline, it doesn't work. So for zero-day attacks, zero-day attack doesn't matter if my baseline says it shouldn't matter. If I don't allow that explicitly, you're not going to run it no matter what leak exploit you have. If it violates the policy, it will be rejected. So the cool thing relative to kernel, kernel tuning, like we saw before, is SE Linux actually has a whole tunable subsystem as well. It has booleans for certain things. It has context that you can edit and kind of manipulate. In line 9, 10, 11, you can see that we changed the context for HTTP port, which, as you can infer, is related to the port that HTTP can use with Apache. So we set it to 81, we restart Apache, and now, lo and behold, that we can actually do this again. So you've tweaked the policy to allow this new thing that you wanted to do, but until you tweak the policy, it won't work. Hacks gets into kind of the nitty-gritty part of preventing attacks. The types of ways an attacker will leverage a vulnerability obviously vary greatly. Things at like really low level, like return to libc, and your ROM gadgets, and all these like really technical things that I'm sure some of you know a lot better than I do. These different ways that an attacker leverages vulnerability to actually form an exploit that will actually execute and work is kind of hard in a lot of cases, and it's really hard if we actually restrict what the kernel's going to let you do with that binary in the first place. So I compiled a literal buffer overflow. I could have just mocked this up, but I took the time just to write a buffer overflow vulnerable binary and actually compile it and test it. I have a buffer overflow binary. I execute it. I overflow the buffer, and it says killed. It doesn't say segmentation fault. It doesn't say anything else. It says killed, and killed for a defensive person is great. We like to see killed. So we looked at our kernel log, and we're able to see that packs terminating task. It has the path to the file, it has the PID, it has the user ID, effective user ID, all that information. So what we know what happened is that buffer overflow ran, but it didn't run in a I executed properly type of context. It ran in the I got as far as the kernel said I could get, and then it killed me. So if you take something like buffer overflow, Or, and it's kind of an eye chart, I apologize, or you take one of these other examples where it says killed next to, all those places that it says killed are different ways an attacker will not be able to leverage to actually execute an exploit against your system. Now, some of you might not know what half those things are, maybe none of them. What you need to know is there are finite ways that most attackers can write a vulnerability, or write an exploit for a vulnerability. And that most exploits that are written are write once, ship it, put it on a packet storm, and everyone else downloads it. I mean, that's the reality of attacks, or goes to the Metasploit or whatever. We don't have like dynamic, most people don't have dynamic exploits that are going to be like, oh, I see you block return to libc, therefore I'm going to do whatever else. That doesn't happen that often. Yes, if you're a hugely valuable target, you might actually see some custom exploits, but probably not. That guy's got a phone call in the second row, which is kind of weird. So reconnaissance is one of those things that an attacker, if they're looking for ways to exploit a system, they absolutely need to know what to exploit. If you don't know what to exploit, what are you going to go after? So if we look at the top line, and sorry I had to do this, I wasn't going to copy and paste all this. Dmessage, basic kernel output, what's happening when you boot a kernel or boot a system up. It has good information. It has stuff that you might go, oh, hey, there's a device driver in the kernel I know that I can attack, or some other information like that. The other thing that's really useful, and a lot of exploits actually use proc for memory address space for different ways to attack. This is kind of a fuzzy math way of looking at it because proc has like recursion and other stuff going on. But anyway, so there's 110 things. They're folders or files. Proc's metadata. It's not a real file system. It's a pseudo file system. So what you need to know is there's 110 things to start. That's the important part. If we drop privilege to our unprivileged user, we try to do proc, and we see that you went from 110 to 58 things. And then you see that dmessage can't be looked at by that unprivileged user. So in terms of reconnaissance, I've dropped dramatically the amount of visibility an attacker has into a system, which sucks for them, but it's great for me. And I've also reduced just in general, overall kind of knowledge of what a system might be doing. Here's a much more salient way to point this out. If we're logged in as root and we look at kind of a quick process count, we see there's 59 processes running on the system. If you go to your unprivileged users, or your unprivileged user, you see 9 processes running. You can only see, and this is just a GrrSecurity, kernel enabled thing. You can only see the processes that your user owns. So for an attacker, if they don't know what I'm running, and they can't demessage, and they can't look at proc, which proc really has a lot of correlation to this, that really reduces what the potential attack surface they're going to go after is because they don't know what to go after, which is great. Earlier we saw the bash history thing, which is a funny thing, and there's a lot of ways to get around it, and it's good to know about it. It's a good example of how file system attributes work. The real way you want to log data about what is happening in a system, there's an entire kernel subsystem for auditing. It's called the audit subsystem. This subsystem is logging, or it sees everything because it goes through the kernel, right? It knows about every single syscall you're making, it knows what files you're looking at, it knows what directories you're in, it knows everything. And if you imagine how powerful this is for a defense to have, if we look at something like temp, we know that temp is a huge part of attack surface. We know that if we don't manage it correctly, a lot of attackers will go after temp first. So let's watch temp using the audit subsystem. And there's just this userland audit control, basically. We set a watch directory and we set a key for it effectively. If you notice, I just do a quick ls temp and that's it. That's all I did for that entire thing. The output you see there is only like 2 of, I think, 5 or 6 pieces of output from that single ls. So if you want to know granular detail about what is happening on a Linux system, this is the way to go, right? I see, let's pick things out. I see inode data, I see ownership data, current working directories, architecture, what syscalls ran, whether it was successful, what the exit code was. If you want to do forensics on what happened to a system, you can imagine this is an awesome way to find out. Because in history files, once a box is compromised, right, you lose that real integrity. So what's important here, and I wrap up with this as well, if we get that far, is you should be remote syslogging all of your important log data. Your remote syslog box should not be like a 9 like service, oh, it's my web server too, and oh, there's a IMAP server on this as well. You should have a remote syslog server that only does syslog, and only accepts syslog, that's all it does. Because at the end of the day, if someone does compromise this box, these log files that are tenant on the system don't mean a whole lot. The only thing you can really trust in is if you get this log data real time, and then you see the attacker on there doing bad things, and then you see the attacker deleting these log files, you'll see all this actually come over, and they can't stop it necessarily, because by the time they get root, or privilege in general, it's too late for them. Once you have root, I've already seen all the ways you got root. I've seen the ways that you escalated privilege, so it's too late for the attacker at that point, which is big help for us. All right, we're running out of time. A couple more things. SFTP, as of a couple years ago, actually has native now shrew capability. So if you log in as a user, normally you log in, you have the full Linux file system ahead of you. You can, cd ... you're in the home directory, you can type ls and see all the other home directories, right? Once you shrew, all that does is changes root for your home directory to be the root of the file system in the eyes of your SFTP. So if your users have really bad discretionary access controls that would otherwise let me log in to the SFTP, go in their home directory, download their files, by doing the shroot, we actually restrict them to not be able to do that because you can't get out of your home directory. That is your root now. So a really simple thing, it's like a 2 or 3 line turn on of a SSH config now. Two-factor. You're supposed to cheer. Yeah, good. Kevin's probably gonna punch me because I have the old screenshot here. He works so hard on all the beautiful stuff we have. So it's great that you want to stop brute force attacks on SSH. It's awesome that you want to have awesome passwords. It's fantastic that you want to use port knocking. Those things are all fine. But what you should look at is what is going to be the most effective security mechanism that is the hardest for an attacker to defeat, that is the easiest for you to implement. And as a representative of Duo Security, I'm going to say Duo Security. Two-factor authentication, you guys have seen it. LinkedIn has rolled it out, Twitter's rolled it out, Evernote's rolled it out. It's not going away, it's only getting more broad. And the idea is, if you have PCI compliance restrictions, you have probably looked at 8.3, which talks about strong authentication, two-factor. Some of the HIPAA guidance, high tech and similar stuff, you're going to see this stuff popping up more, and the further we go in terms of regulation, two-factor strong auth is going to keep popping up. So, with Duo, and you can come to we luckily have a vendor area, usually I have to explain this more. Come to our vendor area, you guys can see a demo hangout, free to 10 users, and we actually are doing a drawing for 100 users for 6 months for free, which is like $1,800 or something crazy. So, you go hang out with our team, because we're going to be here all week, and we're going to be doing a lot of demos. All right, so I want to finish up really quickly, because I think at the end of the day, the real life stuff is what really resonates. Shared web hosting company, customers are supposed to open their own server on their own IP, or on their own port for their own IP. It's a LAMP stack, Linux, Apache, MySQL, PHP. And you patch the system, that's great. You have an egress firewall, that's great. And this is kind of a 1 and 1.5. So 1 is the attacker has a kernel exploit you don't know about, and they have a SQL injection. Sound familiar? And 1.5 is they just have a password for a user, which happens all the time, right? We see breaches constantly. So here's some PHP code. Here's a vulnerability in a SQL query in my PHP code. Here's me writing a command shell in PHP to the file system in a writable directory. Here's me using that backdoor to wget that kernel vulnerability or that kernel exploit we talked about. I'm compiling it and I'm executing it. And now I have access to whatever port I can find that was open. And a lot of people say, well, if you have good ingress firewall rules, then there's no way you can open, connect inwards because there's not going to be a rule for that. If anyone's ever done anything with any exploit, reverse TCP shells do a lot of cool things. I don't have to let you call in, I can call out to you and open a shell all the same. So firewalling's good, I'm not saying firewalling is bad, but if you have any ports open, you're probably going to be hosed. To be fair. You have DNS, right? You have HTTP, you have whatever. There's going to be a port open somewhere. All right, so if we had no exec on home and temp, they wouldn't have been able to compile and execute that code, so they wouldn't have the kernel exploit work, and they wouldn't have privilege. If you had restricted your users to kind of lock them down, you could have actually excluded them from opening any actual ports to listen on in the first place. You could build it with your kernel with packs and possibly prevent them from actually even executing that kernel exploit, even if it is unreleased, it is 0-day, they have an exploit no one else has. You could still stop them just with packs. And then if you want to kind of get around some of these other issues, if you enforced all users to go from one web server, you could actually lock down all those other users from actually doing any network kind of operations at all. So attack 1.5 is much simpler. You log in with the credentials you've stolen, you upload the vulnerability executed, and you're done. Port knocking, they wouldn't know there's SSH to log into. Cracklib, they probably wouldn't have cracked that password so easily. If you gave shrewded SFTP access to this web server, like you only need to upload files to this web server probably, right? Because it's a web server. If you didn't give them a full shell and you gave them shrewded SFTP, there's no way that I know of using SFTP to actually execute commands. This isn't SCP, this is SFTP. And with that, there's no ability to execute commands because it's a complete different subsystem. And if you use two-factor, those other things don't even matter, because if they stole your credentials, unless they stole your phone at the same time, they're not logging in. So utilize remote syslog. If you don't do it, the compromised logs are going to be kind of useless. SE links and GrrSecurity, they do take some effort. It does take some time, in some cases, to tweak the policies and make things work for you. In my experience, the SE Linux policies that roll out with distros these days are really, really good. I mean, I've done like Drupal, MySQL, stacks for web servers and other random things, and SE Linux just works out of the box, which wasn't the case 5 years ago, I assure you. So try it again if you've gotten sour on SE Linux a while ago, or AppArmor, or GrrSecurity, RBAC or anything else. Untrusted users, log as much as you functionally can. I realize logging takes space, and space takes money, and bandwidth and everything else. But if you have untrusted users, especially like a shell hosting company, get some insight into what they're doing. Don't trust their logs and history files. And a shroud isn't necessarily always going to be security either. And the reality is SE Linux has had vulnerabilities against it, and GrrSecurity has had issues, and shroods can be broken out of, and all these things can happen. So again, if you don't layer and you say, oh, I have SE Linux, no one's going to break in and own me, or no one's going to compromise me because I have a firewall with UID match rules. Like, there's a million things that you can hope for, but again, if you're not layering, it doesn't matter. So I have 2 pages of references. All these kind of things are discussed in these, and that website has all my slide decks, so if you want to check this deck out online, ask me questions, email, Twitter, and I think I'm done. Thank you.